Electricity question 3. Claire has a light bulb inside her car. The light bulb is labelled 12 volts 5 watts and is connected to the car's 12 volt battery. Describe what the label means. It means it should be run at 12 volt supply across the light bulb, and that at that 12 volts it will run at 5 watts, that is 5 joules per second of energy converted into heat and light. B. Calculate the size of the current in the light bulb when it's switched on. We've got P equals I times V. So we've got the wattage and we've got the voltage. So we can find the current I equals P over V, which is going to be 5 over 12, which equals whatever you calculate it to be. I'm not going to do the calculations because it'll take a little bit long and it's a long question. Claire wants to replace the light bulb with a pair of LEDs. An LED is a diode that can emit light when there is enough current in it. The LEDs are designed to operate at 3.4 volts, so there's 3.4 volts across them. She sets up the circuit as shown below. Explain in terms of resistance which diode has the current in it. Now that is interesting because in terms of resistance, diode B is pointing the wrong way, so B is the wrong way. In terms of resistance, that means B is infinite in resistance. It's not actually true, because if you get about 500 volts across B the wrong way, it'll still conduct. And A has the current passing through it. So A is current, and it is, once it's conducting, it's essentially zero resistance, vanishingly small resistance, and it'll allow whatever current to go through it if you could increase the voltage. But thank goodness there's a resistor in there as well, because it can't increase the voltage across that. Now Claire rearranges the circuit as shown below. She includes the resistor to reduce the voltage across the LEDs to 3.40 volts. Good idea to note what she's changed. You can see that the battery is around the other way. I'm pretty sure it's around. Oh, I got it wrong on this one. It'll be A that doesn't conduct and B conducts, and for the reasons I said below, I should have taken note of that. So the only change in this circuit down here is the battery's still around that way, but we've changed the diodes to be both pointing in the correct direction. So D is asking you to calculate the voltage across the resistor. This is a very easy one because we were told it's 3.40 volts across here, so it's just 12 minus 3.40. And it says write answer to the correct number of significant figures. When we're adding or subtracting, we have to stick with the least number of decimal places. So being a bit of a tricky one, this is not a multiplying or dividing, adding or subtracting. We're limited by the 12 volt one. So we're actually going to have to round to the ones column. So let's see, 12 minus 3.4 is 8.6. 8.60 if we go to the, but we can only round to this column. So it should round to 9 volts to 0 dp. So that's a bit of a tricky one. If there was multiplication or division, we would go to 2SF because 12 is the least number of SF. But moving on, E. Claire wants more light, so she adds a third LED in parallel with the others as shown below. Explain what happens to the voltage across the resistor. Well, there is no change because the voltage drop across here is still the same. So no change. LEDs have a constant voltage drop. And if you wanted to get into detail, you could talk about it in terms of resistance. That clue was there earlier about resistance. You're not actually affecting. This is kind of a tricky. If they were resistors, you'd be decreasing the resistance over this section, and therefore that would decrease the voltage drop, increasing the voltage drop across this resistor. But that's not the case with LEDs or diodes. They don't operate in the same way as resistors. I think the answer actually neglected to take this into account. If you look at the marking schedule, what actually happens is you're going, because of the nature of the LEDs with their characteristic curve, they conduct a huge amount of current as soon as you make the 3.4 volts, or 3.4? Yeah, 3.4 volts across. There's huge amount of current. So having an extra one in parallel here is not going to affect the amount of current, because you're pretty much, even with just the two, you're going to tap out the amount that can pass through. The resistor here is still going to limit the current. This is a really tricky situation, and it's a little bit unfair to be in an exam of this level. But yeah, I'll just make a nice big mark there, so if you're zooming through you can check it out. That's a bit of a dangerous one. Moving on. The graph below shows the voltage current characteristics for an LED. So this is the voltage on, I drew the graph above differently. This shows the voltage on the vertical and the current on the horizontal. It says calculate the resistance when the current is 700 milliamps. Now the gradient, remember, from I equals V, R equals V over I, the resistance should be the gradient of this graph. Notice I'm going to highlight, let's go, 700 milliamps is here, so this is the point at which we need to find the gradient. We have to be careful, because if we were just to do rise over run V over I, which is about, say, I haven't drawn that very well, but say 3.5, so it was 3.5 volts, and this is 700 milliamps, we can't just go 3.5 over 0.7 amps, because 0.7 is 700 milliamps. That doesn't work, because that would be like saying the line went like this, and it doesn't go like that. We're not after the resistance which would, from that gradient. That would be an ohmic conductor that has zero resistance, zero current at zero voltage. This one, we actually have to take the gradient at this point, which is roughly there. So we draw a tangent to the line, which is what the gradient is at that point, and then we do the rise over run for that. So we would say, pick, if I've drawn this roughly, say that's our triangle, the rise is from 3 to 3.5, so 0.5, divided by the run of 0 up to 700 milliamps, which is 0.7 amps. Because remember, SI units, volts over amps, not volts over milliamps, won't work. And 0.5 over 0.7 is approximately 0.8 ohm. No, it's very low. It's below 1 anyway. You can put that in your calculator and find it out. Describe how the resistance changes when the current increases. Okay, let's go back up to the graph. As the current is increasing, you can see it starts here, and then it moves to here, and then it moves to the line we just drew, and then it gradually evens out. So the resistance being the gradient, that is the rise over the run or the slope, means it is vanishing to zero. To zero resistance. So it's decreasing. Okay, that's a description as it's decreasing as the current increases. There we go.